Okay.
Okay. Why don't you go ahead and start, Steve?
Okay. Um, let's see. I have hopefully about 5 minutes. And now I just need how to find okay, how do I share my screen? There's supposed to be a button that says share my screen.
Well, they move it every time they do an update.
Yeah. And I just downloaded this today. Share. There it is. Sorry. Takes so long. And then every time I do this, I have some odds and ends I would like to share with people. And so I call this January odds and ends. And that's a picture of the Hubble 35th anniversary NASA Sky Challenge certificate. And if you were to participate, you would get something like that. And this happens to be what the January one looks like. And I'm thinking, well, first off, I'm going to talk a little bit more about that in a second, but ultimately there are going to be 12 of these this year. And so it's going to change from January to February to March and so on and so on. And I suspect that they're going to change those kind of pictures. And in this little 5 minute thingy I'm going to do here, I will tell you that I have a number of hot links. And if you would like to visit those hot links, if you would go to that URL down at the bottom, tinyurl.com/Jan Digital SIG, you will be able to click on those hot links and then go wherever you're supposed to go. Astronomical League news. First off, they did have posted on the website that they're changing publishers. Whoever does the reflector, obviously it's getting higher and higher in costs. And so they found somebody who's going to do it for cheaper. But ultimately, they're not going to get everything converted over to the new software and stuff until later. So if you're a reflector watcher and you get it delivered to your mailbox, it is not going to go by the United States Postal Service for the spring issue. It's only going to be digital. And so if like say the 1st of April, you'll say, hey, where's my reflector? If you go to the Astronomical League site, up at the top, there's a banner bar. If you click on reflector, you should be able to see the March issue of the reflector. They also have the ability, I think, to turn off your mailbox delivery. And I think that they would appreciate that, if for no other reason, that for everybody that they turn off, they'll save just a little money. Somebody said something about sketching. Oh, that was JT about sketching. They, for the last 10 years, have had a sketching contest. And ultimately, there's another one that's now running. The deadline for a submission is March 31st. And so ultimately, if anybody's a sketcher or knows anybody who's a sketcher, tell them about it. And I don't think they get a whole lot of submissions. So there would be a possibility that you could win an award. Ultimately, if you do outreach, there's a Hubble 35th certificate that can be found. It looks very much like that first picture I had shown there, except instead of saying completing, I'll think it says for participating in or something like that. It's color, and I suspect they're going to change it every month. But it's a case where if you would do outreach for a classroom or something, you have 30 of them printed off or something like that, and you get each kid one or something like that. Every year, the Astronomical League has a convention, and I think I mentioned this before, but it's going to be at Ruby's Inn, and Ruby's Inn is just outside of Bryce Canyon National Park. It's like maybe 100 yards away. Ruby's Inn is like a full featured place. It's got everything. It's got hotels. It's got campgrounds. It's got restaurants. It's got a fairly even decent store where you can buy food and stuff like that. Ultimately, if you're interested, there are the dates, and there's a link to a flyer that'll tell you what you have to do to join. If you've never been to Bryce Canyon, it is a most wondrous place. About 10 years ago, 12 years ago, they had an Alcon there. Grant went, and he really enjoyed it and enjoyed the views. I've been to Bryce Canyon 4 or 5 times. They say that on a good, dark, moonless night at Bryce Canyon, you can see over 7,000 stars. And so ultimately it can get really, 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 really dark and you see lots and lots of stuff. And ultimately you'll see so many things. Did you really have trouble finding, sometimes some of the marker stars you're looking for? So anyway, that takes care of some news. Then there are some challenges that are going on. Ultimately, they have two different kinds. At the top of that, it talks about astronomical league challenges. Down at the bottom are NASA related ones. The AL challenges at the top. If you complete them, you would get a certificate from the AL. It will be emailed to you. Number 10 there is called 10 because they've had 9 other ones before it. And it has to do with T. Corona Borealis. And ultimately, that guy is supposed to pop off sometime. And, originally it was supposed to be September. Ultimately, somewhere on the AL site, there's something that says, maybe it's not going to be till April. So anyway, if you're interested in that, go out and take an image of the thing. And if it ever does pop off, then all you have to do is do a second one and you can send it and you get a certificate. And then currently there is another one going. It's number 11 there. They call it the Solar Maximum Observing Challenge. And ultimately, that's where you make a pop bottle magnetometer. They have directions on the Astronomical League website for how to do that. I think you make 50 observations or you make observations for 50 days. I forget, whichever it is. But anyway, there's a deadline for that of April 30th of this year. And down at the bottom, they have 2 different NASA observing challenges and special awards. On those, I do believe you will get both a certificate and a pin because NASA's got the money and they will be able to do that. The first one is called Parker Solar Probe 2, and I think I talked about that last month. Ultimately, you're supposed to have collected the data already, but the submission deadline is January 31st. So if you did take a picture of the sun, during that time, finish up the work and get it submitted. And then down at the bottom, number 12, the Hubble Telescope 35th Anniversary Challenge, I have more words about. And so ultimately, there are 2 levels in that program, a silver and a gold. Okay, if you choose to do the silver, they actually have 12 different challenges that are going to go on during the course of this year. Each month, there's going to be a new list of targets. And for the silver level, you image one of the targets every month, and you do an outreach every month, and then you send it in by the end of the next month, and then they would email you a certificate. And again, the certificate there looks a lot like that first picture I had on that welcoming screen here. There's also a gold level. In the gold level, you have to do each of the monthly challenges. As you do the monthly challenges, instead of only doing 1 image per month, you have to do 4 images every month. And then ultimately, you need to also do 4 outreach activities per year. They would encourage you to do more, but you only have to do 4 for that. Ultimately, every month there's a deadline. The deadline is the end of the next month. So for the January one, you got to turn your stuff in by the end of February. To do the February one, you got to turn it in by the end of the March, and so on and so on. And then for the gold, you do that at the end of the year. Every month there's going to be a new list of targets. They have something that's called the Northern List. It's available for Northern Hemisphere observers like us. There's also a Southern List. The Southern List isn't too much different. And I got the targets here for what they are for January. Obviously M1, I left there's M42, M43, M78, M79, Caldwell's 46. And then ultimately, they haven't released the February targets yet. And when they come up with the list of February targets, I will be very happy to post them to St. Louis Astro, and I'll do it to this digital SIG group. So if you're interested in doing it, you'll know what the targets are. There is one additional requirement, and that requirement is to show where the Hubble image is within your image. And so I got a little picture over there. That is, I believe, Caldwell 103. It's on the southern target list for this month. It's the tarantula. And ultimately, that was taken with the SLU telescope that is in, I believe, Chile. I don't think I did it with Canary Islands. And anyway, ultimately, the field of the big thing is like 43 by 43 arc minutes. And you can see that the Hubble field that I drew in there is a whole lot smaller. You might say to yourself, how will I know what the Hubble field is? Well, that's where these links over here are. And I'm just going to click this first one. And if you would click on that link, Can you see that? Did it go to that screen?
It didn't.
It didn't. Oh, well, it did on my computer. So you go ahead, and when you load this thing up, click on it, and it takes you to the Hubble Messier catalog. And ultimately, you can scroll down, and they'll have all 109 of the Hubble images of Messier. And if I go back over here, if you would then click on the Caldwell, it'll pop all 109 of the Caldwells. And then there's some information about the Hubble telescope and that sort of stuff. So click on those links, and it'll actually take you to the real life kinds of things. If you choose to do it, how do you submit it? You got to do an outreach event. And for that, you tell when you did it, date, time, what was the activity? It's like I blabbed to the digital SIG group about this kind of thing. How many people are there? Well, tonight, I think that I saw like 14 or so of us here. And then for your observations, if you're going to take the one image or if you're going to take the four, what are the dates and the times? What kind of instruments and filters did you use? And then ultimately, you could sketch it, but I suspect we're imagers. You're going to do that. And then that's the email address of the guy you're going to send it to and say, hey, I completed it. Oh, I'm wonderful. And then the good news is you don't have to really be an Astronomical League member. And I will tell you that if you're a member of either ASEM or SLAS, your membership there qualifies you as an Astronomical League member. And then there's a URL down at the bottom. And the URL will take you to the page that talks about all the NASA observing things. And to see the actual stuff here, you got to scroll down some to be able to see it. Ta-da! Hey, we talked about SeeStars a little bit earlier, and I sent this out to some people, but I don't know if I necessarily did it to everybody. But the SeeStar app got updated last week. There's a new version that's out there that's wonderful. Ultimately, it now has provisions so that you can enter a plan and you can plan your night's activity. It's really, really easy to use. It helps automate things. You can literally, I think back to the days 10 years ago when Jim Rowe was doing variable stars using a C14 at Brownell-Sick. He literally was followed during the course of the year, 70 different variable stars, and obviously not all are around it. You could see at the same time. So as the year would progress, he'd knock one off the top of the list and add a couple of more to the bottom. Well, literally, you could do that kind of thing with a SeeStar. You can do it before this update by individually having to say, well, I want to go to the first one. No, I want to go to the second one. No, I want to go to the third one. Now I want to go further. But literally, if you would make a plan, you could have a plan with 20, 30, 40, 50 of these in there. And you could just say, okay, now go do it. And then you go inside and you go to sleep and you sleep all night long. And when you wake up in the morning, it's all done and you would have the data there for you. Ultimately, the only bad thing that I would truthfully say about it is it makes use of the SeeStars. You got to do a 10-minute exposure for the whole thing, 10-second exposures lasting 10 minutes. And so it would be that if you wanted to try to do like a Messier marathon with your SeeStar, this isn't going to work for that. It's because the night isn't long enough, with hey, you're only going to be able to take with 10-minute exposures, 6 per hour, 12 hours, maybe 72-ish or so of the Messier objects. If you're interested in it, if you are a SeeStar user, if you just go to your store and update the software, it'll update it. Now, once you first connect to your SeeStar after you update it on your phone, on your tablet, it's going to upload to the SeeStar itself, to the firmware, and it's going to make some changes. But once it's there, you'll see on a screen, it'll say, oh, look, here it is. And you can see it over here past over here where it says plan, and that's how you do it. Some YouTube videos out there show you how to use it. So it's pretty good. I think it's cool. Obviously, I've made a plan. I've made a couple of plans. On the other hand, I haven't taken my SeeStar out and used it yet because I'll admit it, it's too cold out there for my whole body to go out and freeze. So it's something I want to look at. So I think it's cool. I don't think it's going to help too much to do outreach. And you might say, well, why? It would be great. Well, because ultimately the idea of a plan is you're going to be on a target for a certain amount of time. And when you do outreach, you like to be, I think, a little spontaneous. Maybe you want to go to M42 And maybe, it's like, oh, I've been on M42 for 10 minutes, and then I want to go to somebody else, and here comes somebody up and they want to see it too. And after that, here comes somebody else and they want to see it too. And with the plan, it's like you're set. You got to say, I want to do it with this amount of time. So I'm I'll give you that on using it for outreach. I have two quick screenshots and I'm done. And I would point to the screenshot on the left, on the right, get my directions here right. That's what it would look like when it's running. And the idea is there is a target. I think I did this in order of M42 and then M43. And then ultimately these the vertical lines, they're movable. You can grab them, you can slide them right and left to give the target more exposure time or shorter exposure time. Really easy to set up. Okay. And then this side over here is like a lot of if you're a SeeStar user, you'll recognize what's going on over here. And this is how you use to set it up. And eventually you get it set up and you get the add button. Works great. Anybody need to know about anything?
Yeah. Hey, Steve.
Yes.
It's been a while since I've done anything lately. On that last photograph you showed, where to get M81 and 82 in place, is there a rotate function to rotate that field of view?
Yeah, I don't think it's on. Sorry, my screen's a little bitty. I apologize for this. Yes, let's just put it this way. On the newest software, when you get ready to add, you see like right here, there's a little button that's called framing. Where can you see the mouse wiggling?
No, but if you can describe it, there's a button framing. Okay.
Yeah, as you look at these buttons here at the top.
Oh, I see it.
Picture on the left. The one at the bottom is called framing. Okay.
Yeah.
And if you click framing, it'll give you some new junk down at the bottom. And the junk at the bottom can be used for a variety of things. One of the things is it can be used if you want to do a mosaic. And so you can use it to enlarge, and get a bigger image. But right next to it, there's a tab. If you click the tab will get you to the framing. And at that point, as you slide a slider back and forth, it'll turn that view box to the right or to the left so you can frame up.
Oh, okay. Because that's really nice. That would be really nice for the Leo triplet, and plus there's those other three that are in Leo.
I will tell you that when I did it on mine and I put those two guys in there, I did do the framing. And so if it were really to do this kind of thing, it would come out and it would have M81 and M82 in the same image, like above and below each other. So yeah.
That's fine. Now the update for the newest software, did you go through your app store?
Yeah, Android. I went to the Android. Yeah, I went to the Google store, and it's like, oh, update. Here's an update.
All right. SeeStar S50 update.
Yep.
Cool. Update. Done.
And then once you connect your SeeStar again, it'll upload firmware to it, and at that point, it will be able to do that.
Yeah, I uploaded some software that has the mosaic, and after that, I've not been out at all. I've just been.
Have you heard the bad news about the mosaic?
No, I just hear that it takes a long time.
It takes a long time to do, and it'll just kind of work around and spiral out, and it wastes a whole lot of time.
Yeah, so I guess it's okay if you got one thing you want to do.
I would agree to that.
Yeah. And you're on one side of the meridian, maybe?
Yeah.
Okay. I'm just guessing that would help.
So anybody need to know anything, let me know. Keep the cards and letters coming.
Yeah, the only thing I would comment about the outreach is that I found it very easy to do, at least for the solar program, because all I did is I just went to the library, went into said, hey, librarian, I'm setting up outside with the telescope, blah, 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 blah. It turns out they have, in the summer, they had programs with kids coming in at 11 o'clock to do some things. And so I just hung around, and they would come out with the parents and talk to them about the Parker Solar Probe. So that took absolutely no planning at all. It just went out and set up and had some fun.
Yeah. And again, the only thing about a SeeStar and outreach that I worry about is if you were try to use the plan mode, which is what they call this new thing, that plan
Yeah.
mode. I don't think that is conducive for outreach. But for every other way, definitely.
I don't know.
Yeah, if you're only doing 10,
The
go
way
ahead,
I
Dan.
thought about it was that for people like Twellman and all the other guys that have their own scopes, plus the SeeStar, I thought it would be great for them to just set it up there. And it's kind of like the old way that SLU used to work, where it just cycled through stuff. And you just hand off a tablet or some old tablet or something, and
Mhm.
people see
Yeah.
what it's doing.
Oh, and another thing about the plan is it will save the data to the SeeStar itself, but it doesn't save the stacked picture to the tablet to the phone.
Hmm?
You know, when you use a SeeStar, and let's pretend you say, I want to go out and take a picture of M81. And you stack it and you're stacking and you're stacking and you're stacking and you say, up, that's enough, and you stop, then you can pull that image back on your phone, and you can
Yeah.
see it after it's done. Okay. But when you do the plan, it doesn't save the stacked image to the phone. It only saves all your data on the SeeStar. So you later then have to go hook your SeeStar up to your computer and download the stuff to your computer to be able to see the stuff that the plan did.
Okay. Well, I can see some updates coming.
Okay, thanks, Steve.
Welcome.
Bill, if you want to go ahead and take off. You are muted. There
I'll
you
get
go.
ready. Eric, is this your first meeting, or were you in last month?
I've been in a couple. Sometimes I haven't been in them.
Okay.
I don't think I was in last month's.
Okay, well, that's good. I think you and I have a mutual friend,
Yes,
Logan
Logan.
Sawyer. Yeah,
It's good to see good to see a face now
yeah.
to connect.
Is anyone else this your first meeting or recently started attending? Nobody
I
else?
see Landon's back.
That's great.
MJ and Tally, they're in the observatory next to me in New Mexico, and
Ah,
they join every so often.
great.
2 in a row for me. I think that's a new high.
Right. I found this a really interesting topic. I've been thinking about it for a while, and then I saw that Sky and Telescope had this article, so it really triggered a lot of things. In fact, I posted this image recently, and one of the whole points was I was trying to really better understand some of the issues that were mentioned in the article, in addition to solving some vignetting problems I was having. So the article, if you haven't read it, is in the January issue. I think that the authors posted this on his website since then, but it's written by Ron Brecher, and it's very well written. I thought the thing I liked about this article is it's very understandable. He keeps it simple. And focuses on deep sky imaging with long focal length telescopes. So he's not trying to cover the whole world here. So he's not talking about lucky imaging or planetary imaging. It's really about deep sky. And what he was trying to get at is the right pixel scale or pixel spacing given a long focal length telescope. And he makes the point that there's no one camera that's ideal for all of the conditions we might encounter. But I was really impressed with the way it was presented. I've seen a lot of really complicated methods, and this one kind of stood out. But his basic conclusion is that you need to understand the pixel scale of your system. So pixel scale is the arc seconds on the sky side per pixel in your image plane. I calculated as 206 times my pixel spacing in microns divided by the focal length of my system in millimeters. I know that's mixing units a bit, but we always talk about, cameras and pixels and microns and focal length in millimeters, so that 206 is a scale to accept that. And not to bore people too much, but it's really important to use your effective focal length. So effective focal length is the focal length that includes all of the effects of your focal reducers, your coma correctors, using a Barlow, and so on. So for my system, is this mine? No, it's close. 1,000 millimeter focal length. So imagine a 200 millimeter at f5. And if you have, I think I have a 0.675. But anyway, if you have a 0.8 focal reducer, that means your effective focal length of your whole system is 800 millimeters. So if you're trying to follow along in his presentation, think of it that way. If you are going the other direction of putting a Barlow in, which we don't do in deep sky imaging, then obviously you would double it. The author is comparing this image scale to the full width at half maximum. So it's the star profile, that would be falling on your sensor. And the way this is drawn is typical. It's this kind of Gaussian shape that we see of stars, and the peak is in the middle, and so what you're looking at is the half maximum width of the star that's falling on your pixel. And so he's defining pixel scale as the relationship between the arc seconds size of your full width at half maximum versus the same size in pixels. So obviously pixel scale is in arc seconds per pixel. He also mentions half flux diameter. I'll talk more about that later. He makes the point this is essentially equivalent to the full width of half maximum. And I did some digging into that, and I believe he's absolutely correct. They're very close, or not exact, but within, let's say, 5%. So good enough. But what I'm finding is lots of users are finding that they're questioning the way the programs are calculating it. And that's my experience. And again, I'll talk about that later, but just kind of keep in mind, if you're trying to follow along with this paper and you look at a full width at half maximum that you might get from, say, PixInsight, and compare it to the half flux diameter you would calculate out of Sequence Generator Pro, don't be surprised if they don't line up. The author also proposes that sampling could be up to 5 times better than the seeing conditions. So I'm taking a rather extreme statement he made. I'm not trying to say, wow, that statement proves him wrong. But I think it was an interesting thing that he said, because it starts to point out some trade-offs. You can go too far. And for at least us in Missouri, trying to do that kind of sampling is, in my opinion, but for my interest, going too far. So he talks about this Nyquist sampling rate, which is something I find interesting. I think he was trying to keep this simple. He didn't want to go into the details, but there's a few details that really are important here, because otherwise it's easy to misunderstand what this physicist Harry Nyquist was trying to say. I'll get to it a little bit more later, but using his sampling theorem incorrectly kind of drives you down a path you don't necessarily want to go. But Harry Nyquist was a physicist and also an electrical engineer. He worked at Bell Laboratory. One interesting story about him is that they were doing productivity measurements, really creativity. What is it about Bell Labs that made some of their staff far more creative than others, and they decided to measure creativity as patents, how many patents they were awarded. And they looked at a number of factors, but as they crunched the numbers, the correlation was strong between those that had a large number of patents than as those that tended to have lunch with Harry Nyquist. And what they found was he was just initiating a lot of really interesting conversation. But he had developed two important laws. One was on thermal noise, and the other one on information theory. And he was trying to do this in the context of electronic communication, right? This is Bell Labs. It's about using sending signals over wires and through transistors. And that's what a lot of his research was that was pioneering and remembered. And he came up with this this famous rule that he proved that the sample data can't be less than twice the rate of the, it should be signals rate of change. So now that's stated, I'm stating this differently than he did in the article, but it's an important distinction. So what he was saying is if I've got a wave I'm trying to sample over time, and it's some frequency f and kilohertz. In the example I gave here, 10 kilohertz radio wave, then I better sample it at an interval no less than 1/2 times a kilohertz or 5 milliseconds, 0.5 milliseconds. So what he was relaying is your ability to measure a frequency using some kind of sampling interval, and I'll come back to that. But physicists applied that theory to optics, and they changed frequency to say spatial frequency instead of time-based, and then everything he developed was very applicable in our world. So when I look at my system, and if I literally followed some of the extremes that the author proposes, I got a 200 millimeter aperture, f3.75 system, so I have a 750 millimeter focal length. If I had 1 arc second seeing, now again, the author mentions it. He doesn't say you're going to get that. In fact, I think he says you're going to have worse than that. But 1 arc second would be really excellent seeing. And that equates to, for me then, a pixel scale of 0.2 arc seconds per pixel. And my pixels, I'm sorry, that's pixel scale. So the pixel spacing to take full advantage of that 1 arc second seeing condition would be 0.7 micron pixels. And if I could find a camera that would do that, maybe one out of a mobile phone, I wouldn't want it. It would have other issues. But it made me think about how when I think about what the author's saying, I need to be careful about it because he's saying under certain conditions with certain assumptions, and I have to modify those assumptions to my reality about my kind of mount, scope, and seeing conditions. Otherwise, you get driven down the path that smaller pixels are better. And my experience is smaller pixels are not better. So I want to revisit some of my assumptions. So I'm doing astrophotography, and I think we often tend to overestimate seeing conditions, or at least I do. And the reason for that, well, I'll talk about it later. There's also much more to this story about selecting your pixel size than seeing. There's the telescope diffraction blur, the shape of that blur. There's defocus and aberrations. There's mount vibration. There's auto guiding errors. All of those things make your blur size bigger and bigger. And that means you're less and less likely to be undersampling. And these are dynamic conditions. So they're occurring over time, and they're changing through the course of making your image. So you really need to think of Nyquist in a statistical sense. And that's the way he really meant for it to be used, is in a statistical way. And the other thing about oversampling is that for us in deep sky imaging, it becomes less beneficial. It's different in planetary imaging. Their significant oversampling is really important, but in deep sky imaging, because of the long exposure times, this oversampling is less important, at least for me, with the kinds of objects that I image. And there's a price to be paid. Smaller and smaller pixels hurt the dynamic range, for one, and also decrease signal to noise ratio. So I'm not telling you something you don't already know. I'm just telling you how I think about the way I want to match up a camera to my scope. So atmospheric seeing, I made the claim that I think we're all probably not really good at estimating seeing. At least I know I am not very good, and most people I'm with aren't. And there's some reasons for that. Wikipedia has a really good article about seeing and defining it and so on. And they make the case that there's different layers, there's different wind speeds. These are changing over time. The best sites at the observatory limits have seeing conditions such that the resolution of the best telescope on Earth isn't that much better than an 8-inch telescope. And I think people are often surprised by that, but there's the parameter called the R0 of the atmosphere. That is, it's sort of turbulence size of a block of air, and that tends to be in the range of 10 to 20 centimeters. So you're not going to, making your telescope bigger doesn't give you better resolution. It just means you're going to be able to take either a wider field of view or maybe a faster image. And that these variations are occurring anywhere between 100 times a second to a minute. And that's what makes it really, really hard for us to estimate seeing, because our eyes have refresh rates that are typically during the day at about a 15th of a second, which is why most movies and videos are often at a 30th of a second. So it's twice the refresh rate of our eye. Thank you, Nyquist. But at night, our refresh rate drops, and it's closer to 0.1 to 0.5 seconds. So some people claim up to a second, but probably not at my age. And so these higher frequency variations of stars twinkling are missed. And then on the other hand, if I'm taking a 10-minute image, I'm not staring at a star for 10 minutes to see if I can tell if it moved or not, but it's moving over the course of minutes. And I don't often think about that as being rolled into seeing, but it is. And if there's wind gusts, I mean, that definitely makes the blur size bigger. So I think the author's right in that if we think we're under great skies, great seeing, I have 1 arcsecond skies, it's probably closer to 3. Missouri is particularly difficult because of our low altitude. So we're looking through almost the maximum amount of atmosphere you can look at unless you're at the coast. The high humidity makes it even worse because the moisture increases refraction, and that increases the strength of the seeing problem. And then the jet stream is a problem that frequently moves over Missouri. And although you don't maybe necessarily see it, it has a significant impact on seeing in the upper atmosphere. So if I factor that in, I was looking again at my system, and on the left is sort of if I blindly follow the more extreme example that the author presents, which is a 1 arcsecond seeing, and don't think about some of these other factors, then I get that my spot size will be 3.6 arcseconds, and if I want to be 5 to 1, you can see where I get down to a pixel size of less than an arcsecond, or less than a micron, excuse me, less than a micron. But when I factor in other things, and one being, and a very important one, is the spot size of my telescope. And the author talks about it, but really focuses on seeing. But spot size is really important. For me, that under a perfect, if my system's perfectly aligned and the mirror's in perfect shape, my focal reducer's perfect, I'm going to have a spot size of 1.4 arcseconds just from the diffractive nature of light. Auto guiding, I've got that down to about an arcsecond, and I'm assuming that's including mount vibration, so I don't break that out separately. And then that should be seeing. I'm going to use what the author said is where most of us are probably closer to 3 arcseconds. And then there's other. focus is we never have perfect focus, and it's changing over the course of the image. Aberrations are occurring and so on. I don't have a perfect mirror, so I'm going to throw in another 0.3 arc seconds. So if I roll that all together, that comes out to the 3.5 arc seconds. So you can see right away, I'm not looking at 1 arc second seeing as dictating what pixels I'm going to pick. It's going to be closer to 3.5 arc seconds. Now, if you add up my numbers there, you see it doesn't add to 3.5. The proper way to bring together these varying parameters that are time varying and independent is to RMS them. So you take each one, square it, add it to the next one squared, to the next one squared, to the next one squared, and then that sum you square root it. That's the root mean square. So that's where the 3.5 comes from. And I go through a really ridiculous statistical argument on the right if anyone cares, but you don't. And then down below that, I converted that then into microns. So you see my long exposure spot size is, I'm going to guess, 12.6 microns. And so I should be thinking about the right pixel scale based on that spot size. Now, if I look at a different system, I get a different answer, and the author talks about that. He's clear about talking about longer focal length. If I look at a shorter focal length system I have, so this is an 80 millimeter focal length. The effective focal length, including the focal reducer, brings it to 380 millimeters. Then my spot size is from diffraction is 3.5 arc seconds, so it's double. My guiding is worse because this mount is not as good of a mount, so I get more guiding error. Seeing, I would assume, is the same, and my aberrations are about the same. So my spot size is bigger. It goes from 3.5 to 4.9. But when I convert that to microns, it's smaller for just the reasons the author mentioned. My image scale is lower. So the point he makes and that I'm making here is if you have a shorter focal length, the biggest thing that went down through this whole thing really is the seeing. The seeing went down by a factor of 2 in terms of its impact in micrometers in the image plane. So in this example, I can and do use smaller pixels. On my long focal length system, I use a 5.4 micron pixel. In this shorter focal length scope, I use a 3.75 micron pixel. I find that the PixInsight subframe selector can really be helpful. How do you know if you're oversampled or undersampled? So I recently took these images of the cluster NGC 7789 at 10 minutes luminous exposures. I had PixInsight measure the full width half maximum at 2.54 pixels. That's 13.7 microns or 3.8 arc seconds. And that's within 10% of that table I showed earlier where I was trying to estimate from various factors. So close enough. So by this measure, I am 13.7 divided by 5.4, 13.7 microns. Spot size divided by 5.4 micron pixels, or 2.5x oversampled. And that's, I think that's ideal. And that's in Missouri. And that falls in line with what the author suggested. I was also digging around different websites, and I was surprised and pleased to see that ZWO is good about this too, because ZWO offers some cameras with some awfully small pixels. And even they say, hey, you really got to depend on the focal length of your telescope, and they provide these examples of what they consider undersampled, oversampled, and suitably sampled. And so I've got my image, which you get of the way I got this image was I used the point spread function tool in PixInsight, got a point spread function that's essentially equivalent to the very smallest star size you can really get. And I was pleased. I think I am right in that range. I would say a little bit to the right of oversampled in that suitable sampling range. So my point here is, I think my estimates are probably correct. I think in terms of the blur I have at my site and with my equipment, and that falls in line with what the author is suggesting as well as EWO. And surprisingly, though, I did find that if I use the in Sequence Generator Pro, they use half flux radius instead of half flux diameter. And what I found is half flux radius lines up really, really well with the full width of half maximum. But it shouldn't. It should be different by a factor of 2, but it isn't. It's almost always the same. And I've noticed other people posting on cloudy nights that they see the same in Nina. So I don't know what's going on there. I think either the software, I think most likely what's happening is the software is doing some filtering to get rid of noise, or it isn't doing filtering and is oversensitive to noise. Anyway, I think it has to do something with the thresholding algorithm that they're using, or maybe the stars that they tend to select are too big. I don't know. It's just a word of caution. I would just say pick one you like and go with it. I like the half flux radius. I think that works well, radius out of Sequence Generator Pro, but if you really want a robust calculation, probably the full width at half maximum that comes out of PixInsight's a good choice. Now, I want to go back to our good friend Nyquist, because I said, I think people, and including me, I often misstate what he was trying to get across. And it's really important to kind of walk through the way he would look at this question. He would say, imagine there's 2 stars, and those 2 stars are separated by 5 arc seconds, and I want a system that can split those 2 stars. And I have a telescope, and the pixel factor of that telescope is 0.5 arc seconds per micron. Okay, then now I shouldn't call this pixel scale factor. I should probably call that a telescope scale factor, but you get the idea of relating how many microns on my image scale relate to. No, that's the same thing, of arc seconds in the sky. So yes, that's the way the author was defining it. So the way Nyquist would look at it is to say, this is a spatial frequency. There are 2 stars. So there's one full cycle from bright to dark to bright at 0.2 per arc second. So 1 over 5 is the spatial frequency or angular frequency in the sky. There's 0.2 double stars per arc second. And if I want to detect that kind of spatial frequency or angular frequency, then I need to sample that at not more than 1 over 2 times the 0.2. And then I've got my conversion here of 3.63 microns per arc second, which is for my telescope. And that gets me to 9.1. So if I want to split a 5 arc second double star, I got to have pixel spacing that's not more than 9.1. And then I'll just at the limit of what I can split. But if you're talking about high frequency, small stuff, really small planetary nebulas, for example, certainly for planetary imaging. If I look at Jupiter, and if I say that I've got a band that's an arc second across, that's 1 pair per arc second, and I need a spacing, and that says 2.5 pixels, but I really should be saying 2.5 micron pixels would be the highest, largest pixel where I could do that. And then at the other extreme, if I'm looking at RGB images where I'm really trying to get color, it's not the luminance channel that has all the information about the detail in an image. So the eye is doesn't really look at color for definition. So that's why we bin. So for a 10 arc second type of goal with an RGB image, Nyquist would say, well, that's 0.1 pairs of brightness change per arc second, and that can be detected with a pixel that's as large as 18 microns. Or you can bin it 2 by 2, which most of us do, and that gets you to 9. either way. So my point here is that when you really think about what Nyquist is saying is, it's not just looking at the limit of your resolution, but what are you really trying to image? And if you're imaging extremely fine detail in a tiny nebula, such as a planetary nebula, or for planetary imaging, then oversampling, or not oversampling, but really small pixels are quite important. On the other hand, if you're imaging more for color and you're not as concerned about the detail, then larger pixels are just fine, and you can bend to get there. So here's one way I have thought through this is, if I have two stars, and in the first example, my pixels are so big that these two stars each fall on a neighboring pixel, then I only see one star, and I only detected one star, one big bloated star. On the other hand, if I divide those pixels by 2, then now I can detect 2 stars, and that's great. But you got to be a little careful because if I shift, you notice I did 2 things. I split the pixels in half, but I also shifted it by half a pixel so that each star was on its own pixel. If I didn't shift it by half a pixel, just divided by the pixels, I'd still see one star, and it would be half as dim, it would be half as bright, covering these 4 pixels. So I didn't really gain anything. And the point around this, again, I said earlier that this Nyquist needs to be thought of statistically, is the night sky is not static. It's not like there's a star and it falls on this pixel. And if I have any maybe criticism of the author, and again, he was trying to keep it simple. I should be careful. Keep it simple, be clear. I'm going into probably way too much thought here than is necessary, but in reality, these stars are moving around, right? The atmosphere is shifting them across the image plane. So I'm never going to be so lucky that the star falls on a pixel or exactly between 2 pixels, but instead it's going to look more like this. These stars are shimmering, and I'm going to get across my pixel row things that go from black to grayish to white to grayish again to white to grayish again, and then black. And that's why we stretch, right? We stretch that contrast to get the black in between. So I think again, it's not that this Nyquist limit is not a hard fall off. You either meet it or you don't, but it gets to be how much contrast between these 2 double stars, or between the dark nebula and the bright nebula, how much contrast you're going to get there is affected by the pixel spacing as well as you're seeing. And again, I'm going to take this example on the left out of the book. I'm sorry, the article. And he kind of shows these stars and says, look, if you got a round star, you're going to get a blocky image if you're undersampled. And if it falls on a pixel versus between a pixel, just like the diagram I showed earlier, you get these different sizes and shapes. In reality, again, I'm going to go back to the ZWO. You see that none of the ZWO images matches up with that diagram. My image is never, my point spread function or my spot never lines up with that diagram. And the reason is that it's not as simple as it fell on a pixel or between pixels, but instead the star's moving around across these pixels, in between, back on one, onto the next one, and so on. So it's more of statistically, are they more likely to fall on one pixel versus the other, and it sort of evens things out or blends things out. So he comments, if you've undersampled, you're going to get square stars. I think we would all wish for that problem. In reality, the stars are moving around enough. It's really not a problem. And my image again in the bottom there, you see that the star's moving around in all kinds of different directions. It's round enough for what I do in deep sky imaging. I'm not going to get a square star. Okay, so I said there's a price to be paid. And for me, the price to be paid by small pixels is one perfect example is dynamic range. Smaller pixels have a lower full well capacity. That is, they can hold fewer photoelectrons per readout than large pixels. People use the example of a bucket. A small bucket can hold less water than a big bucket. And if it's raining at a certain rate, you're going to fill the small bucket earlier. That's a reasonable analogy for some things. But there's really many factors that can determine your dynamic range. But the pixel size is certainly one of them, and becoming the more dominant one. On the right, I just calculated for different pixel size for a CMOS back illuminated camera, pixel size and microns on the bottom as it decreases towards the right. Then you see on the vertical axis is the dynamic range. So 50, or I should say full well capacity. At about 3.76 pixels, a ZWO camera can get, I calculated 48,000. I think they say 45,000, close enough. And then as you go up, you see the dynamic range really drops. There's just, you can't keep as many photoelectrons in the pixel. What that means is if you have a really bright star, it's going to saturate. Or if you have you're imaging on the Orion Nebula and you got a bright region versus a dark nebula, you're going to saturate much more easily with a small pixel than with a large pixel. So you're going to gain some resolution, but you're going to give it up by having the saturation problem. Example I gave here too is if I'm at, say, a 4 micron pixel and I shift to using a 2 micron pixel, the dynamic range goes down by a factor of 4. But the resolution would go up by a factor of 2. And that's only if I'm smaller, I'm bigger than my spot size. So the resolution gain is not as great as is the fall off in dynamic range. I think there's 3 people I know that are still using, me being one of them, still using a CAF 8300 sensor. And one exception I would say by this is you can go to a smaller pixel than the CAF because the new CMOS has they're back illuminated instead of forward illuminated. So they gain in sensitivity and gain in dynamic dynamic range that offsets the pixel drop. And I was again kind of calculating in my situation, I could reduce my pixel size by 50% and have the same or better dynamic range. So my next camera will be a back illuminated CMOS with pixel sizes that are probably closer to 3.75 to 4 instead of 5.4. The other thing I was really thinking about myself over the last several months is, my objective is really contrast transfer, not necessarily the best resolution. In Missouri, the atmosphere is always going to ruin my resolution. There's the best mount, the best telescope, and the best camera are not going to fix that. So I want to get good contrast in the region that I can image. Contrast is defined as your signal minus your background divided by your signal plus your background. So if your signal's 1 and your background is perfectly dark 0, that's 100% contrast. And if you're at a 50-50, then your contrast is 0. And a very common way to evaluate this, and I'm sure many people on this have seen this US Air Force 1951 resolution test target. It's very, very commonly used as a way to test the resolution of optical systems. And it's meant to be a perfect 100% contrast, 3-bar vertical, 3-bar horizontal, so you can look at astigmatism. And each group represents a doubling of resolution, and each individual element within the group is 12%. So if I go from the 1 group to the 0 group, I've doubled the frequency. If I go from the -1 element to the -2 1 element, I've doubled the frequency. If I go from a 1 element to the 1 2 element, I've increased my resolution 12%. I know this is really boring, but bear with me, there's a point. So I'm just going to look at this really, really tiny square in the middle, right there. And I blew that up, cropped it, and I pulled that into PixInsight and convolved it with my point spread, my star size, right, my point spread function. And I simulated what oversampling, nominal sampling, and undersampling would look like. So here in the middle is what my system would do. Again, what I'm blowing out this very, very tiny part in the middle of this test target. I put that into PixInsight. I convolved it with my point spread function from my last set of imaging. And I think we determined earlier, I'm about, instead of 1/2 full width to have maximum 1/2.5. So I'm slightly oversampled. And this is the way this would appear on my sensor. And you won't believe me, but if you really stare at this for quite a long time, I can get to about the 2-3 group. If I oversample and do the same simulation, remember when you're oversampling, you're also oversampling your point spread function. So you can see here I've doubled. I'm 5. I said Nyquist, so I'm really 5 times, so closer to what the author might have mentioned is an extreme example. And now let's look at my resolution. And again, this doesn't show up well in my PowerPoint, but I could get down to the 2.4. Now I might argue I could get to 2.4 on the left and maybe only 2.2 on the right. So that's why I'm saying either way, I dropped my pixel size by half and I got a benefit. But it was somewhere between, well, let's just say about a 20% improvement in resolution. But I dropped my dynamic range by 4. The question is really, what are you trying to do? If resolution is really what you want with tiny, tiny planetary nebulae, then oversampling might be worth it, particularly if they're bright. On the other hand, for me, I know my seeing is going to be crummy, so I would much rather have the dynamic range and give up that 12% or 20% in resolution from further driving the oversampling. On the right is the reverse situation. Here, I'm assuming I'm undersampled. It's as if I bend 2.2 by 2 in my luminance image. And I'm being a little dramatic, but it was almost disastrous in terms of resolution. And you can see there's, again, in my center image, I can see maybe the 2-3 target. No way can I see it on the right. In fact, I think I can see down to maybe the 1.5 target. So I've given up 50% of I've dropped my resolution by 2. And so my message here is, if you're going really in terms of the luminance image, being a bit oversampled is okay. Really, really oversampling doesn't get you a whole lot. And being undersampled really, really hurts. So if you're going to err on one side or the other, right, you can't have an infinite number of cameras with an infinite number of telescopes that kind of match up. Being oversampled is better than being undersampled in terms of resolution. So just kind of tying up that being slightly oversampled is beneficial for me. That's where I want to be. I want to be in that 2 to 3 oversampled regime. That is to say that my pixels are 1/2 to 1/3 my blur size, and that's a benefit. But again, only up to the Nyquist limit. And then once you go beyond that, you're going to see marginal gains in resolution, but you're going to give up a ton of dynamic range and also signal to noise ratio. I don't know exactly how to calculate it for these sensors, so I didn't put it in here. And the seeing in Missouri and really most places any of us are going to image are much worse than we might think. I was kind of surprised when I really looked at this carefully and thought through it that I had convinced myself I had been under 1 arc second skies. not for a 10-minute exposure. It's not 1 arc second. It's at least 3. And telescope optics, the mount tracking, all of that are as important as seeing in my situation. The other thing I want to mention is, excuse me, these programs are not necessarily accurate around half-flux radiance and half-flux diameter. So I don't know if someone else has experiences there or digs into it. I'd be really curious what they find. I'm going to dig into mine and try to learn more. I talked about noise and resolution, and Nyquist would say it's really up to what are you trying to look at. That's what should determine your pixel ratio, not just your seeing. And again, just to beat it to death, small pixels are not necessarily better, and because of the loss in dynamic range with this marginal improvement in resolution. So this is just my take on it. Again, I think the author's paper was very, very well done. It's one of the best I read. I learned a lot from it, and I just had to tailor it to my situation being in Missouri. Thank you.
Anyone have any questions?
Bill, I have
Well-
a comment. With Bayer arrays on sensors these
Yeah.
days, of course, the spacing, I always say that's about, because the Bayer array per color is about half the resolution. That
Yes,
isn't exactly right, but we need to take that into account here as well.
excellent point. I think I might argue undersampling. For me, I've run into this problem where you can get really weird star colors because of the Bayer mask. So, and so if you get a star that mostly falls on the green pixel, it's going to make the star look green. And debayering is not meant for astrophotographers. It's for panoramas and terrestrial and faces and so on. So it doesn't handle stars real well in my experience. And I think being oversampled is much more important in a one-shot color camera because I think the debayering is better handled.
Yeah, I found down in New Mexico that I have a 0.30 arc second per pixel on the color camera. And that works out pretty well because it is oversampling now. And I don't seem to have the problems you described with green stars.
Yes. So let me just mention this one more time, and you guys may, I'd be curious if you think I'm wrong in the way I'm thinking about it is, I got this Bayer mask, and again, if I'm, the way I encountered it is I was just thinking this 1.8, f1.8, 50 millimeter focal length lens to do a constellation shot. And I noticed that, gosh, if I zoomed in, I did get some square pixels, and I got green stars, a lot of red stars, and so on. Remember, there's 2 green pixels usually for each red and blue, so you're more likely to get a green star. It's just really, really wonky. And if you go the other direction, because if the star's falling in one part of the Bayer mask, the whole idea of debayering is to look at the neighboring pixels and kind of vote and try to decide what color this thing should be. And it can't do that. There's only green, so it can only say green. If the star is oversampled, then that star is falling on a range of pixels, multiple greens, reds, and blues, and it can do a much, much better job of debayering to assign a color to that object.
Bill, how does, when you process and you drizzle process, how does that affect the math? Is that an example of more oversampling?
That's great. So the way I think of it is drizzle is a way of oversampling without the loss of dynamic range. It's a way of sort of oversampling without having to go to smaller pixels. I think it's really, really important. That's one reason why drizzle was invented, and is to get sub-pixel resolution. So I joke about this, but it's not a joke. You can auto drizzle, right? The atmosphere is moving stuff around for you, and my mount is sort of moving stuff around, and you just sort of intentionally do that by known small amounts, and yes, you can get sub-pixel resolution without having to go to smaller pixels. And to me, if you that would be my first choice. If I'm imaging small planetary nebulae, you're trying to really get resolution, is I would go to drizzling rather than smaller pixels.
So Bill, one thing that doesn't seem to factor into the calculation of arc seconds per pixel at all is the aperture of your telescope. So I guess that's the way the optics math works out. So how does aperture factor into any of this, but if at all?
It does. And in mine, you notice I said my optics have a spot size. That's where it comes in. I'm assuming light at a wavelength of 550 nanometers. My F number, I forgot, 3.75. So the spot size that is caused by the diffraction of an aperture is 2.44 times the wavelength times the F number. Very simple. 2.44 times the wavelength times the F number. The only trick is put the wavelength in microns. So you get on your image, and that tells you the blur size on your camera. So the bigger the diameter, well, here's okay, but that doesn't fully answer your question, because you said diameter and I said F number. Got to be careful. I saw Dan, you were using Telescope Live. I think the F ratio of the scope you were using was F 3.75. Was pretty close to that, and I remember that because that's what my scope is. So Dan's scope was 3.75. What was the aperture?
I think that particular scope is like an ASA. I think it's a 12-inch. I don't have the information here.
Okay.
It's the ASA 12-inch version Newtonian.
Okay, so if it were 20 inches or 100 inches and it's F 3.75, it has the same spot size as my 8-inch or your 8-inch or 6-inch or 4. If it's F 3.75, it's the same micron spot size on the image array. And I know that seems weird. I have trouble getting my head around it, but it's not so much the aperture as the F number.
Okay, got it. And so really the aperture is just gaining you potential for shorter exposure times, more intensity, but isn't changing the resolution.
Well, I got to be careful. What I was talking about is in terms of pixel size. If you're talking about resolution in the sky, then you need to divide by the focal length, because you're now going to be on the sky side of the thing. So there, it's a slightly different formula. It's 2.44 lambda over d, the diameter. So spot size on the image plane is 2.44 lambda F number. The arc second resolution up in the sky is 2.44 lambda divided by the diameter of your telescope. And again, you got to do them both in the same unit. So you might convert millimeters, and then that tells you your resolution in the sky side.
So in Missouri anyway, for kind of practical use of all this information, you're telling us to lean towards thinking of the seeing, and that you're likely to run across effective seeing is, something like 8 or 9 or 10 arc seconds.
Yes.
Yeah.
Yes.
Okay. Because that's a higher number than you generally see bandied about in the.
It is, I've really challenged myself testing that, and I've convinced myself it's probably right for my site with my equipment. and my focal length and so on. In New Mexico, could be very different. Rocky Mountain Star Stare, where you're up at 7,000 feet or 8,000 feet, less atmosphere, different situation. And the author mentions that too.
Yeah.
You know, he's decided to rig his scope for the best possible seeing. I rig my scope for the seeing I'm most likely to encounter.
Yeah, I'm with you. I'm with you, Bill. I think that's more to the point, probably, for most people.
You know, the other thing, I've been taught this many times, and I always forget it. So it was great doing this presentation because it reminded me the at least in Missouri, there's really no resolution benefit to getting a telescope that's more than 8 inches. You're not going to get any more resolution. I told you earlier that 2.44 lambda F number. Well, that's theoretical if there wasn't an atmosphere. But with an atmosphere, you know, your diffraction from your scope is so small, it's just being washed out by the atmosphere.
Bill, all those like full width half max or HFR numbers you're talking about, are those from a single frame, or is it from a stack, or does it matter?
I think that's really an interesting discussion. I'd be interested in your opinion. I took them all from a single frame because what I was interested in is, you know, for a 10-minute exposure, what am I getting in a single frame? When you go into PixInsight, though, you're stacking, and it's also doing pixel rejection. Well, that might change things, and probably does. And then further, of course, if you go into star size reduction, you know, that's a completely different situation. So it throws everything kind of out the window. I'd just say that I remember this guy in St. Louis, Donald Snyder, is an image specialist. He was well known for developing the algorithm that deblurred this Hubble Space Telescope image when it had spherical aberration. And I once asked him, I said, well, why do we even worry about the quality of optics anymore? Why don't we just deblur everything in software? And he said, because you want the best data to start with, right? If you're going to deconvolve something in PixInsight, you're going to deconvolve it. Why don't convolve it to begin with, and then you're going to get a better result. So, you know, I think the better image, better data you can start with in your subframes. My point is, you're going to get a better result going through the stacking and going through the morphological reduction of star size, and so on, and everything is just going to be better. It's kind of, I think of it like Dan always advises on flats. You can process an image without flats, but boy, they clean up a lot. Well, if your subframes are good, it makes everything else easier.
What about dithering? Is dithering only affecting signal to noise, or is there anything in the math and statistics that dithering increases resolution?
I think dithering is largely a statistical benefit. So we're not talking about drizzle now. We're talking about dithering. So with dithering, the idea there is I've got a defect on my chip or a dust mote or something, a hot pixel. Nah, that's not a good idea. Yeah. I've got some defect in my image plane, whether it's a dust mote, a hot pixel, a dead pixel, whatever. And I'm going to dither my image across multiple pixels. So now I'm not just going a drizzle, a fractional pixel, but I'm going multiple pixels. And then in software, I can say, I can use a median or something to decide to reject the thing that, gosh, this object has a certain intensity on this group of pixels, but when I put it on this group of pixels, I get a different intensity. Or this particular pixel, I know statistically should be brighter than it is. I'm going to reject that pixel. So yeah, it's It's a way of shifting the image over different parts of the sensor, and then statistically saying, again, it just mentally, it's easy for me to think about medians. If I look at the median, I could say, oh, clearly this pixel's too hot or dead.
So it's strictly a signal to noise ratio improvement. There's nothing that you could statistically say is resolution improvement. That's how I'm seeing it based on what you've said, but I'm just kind of confirming my thoughts.
That's my view of it.
Yeah.
It's a noise. Well, noise, it eliminates noise, but more importantly, it eliminates artifacts.
Which is noise as well.
Well, good point.
Yeah. All right. Thanks.
Yeah, Joe, I think that in the older days, I think most people thought that you had to dither multiple pixels to make drizzle work right too. I'm not sure that that's really the case, but most of the time, if you were doing drizzling, they recommended you dither multiple pixels.
They still recommend that. If you
Okay.
go to, and all the drizzle tutorials say, well, use well dithered frames.
Okay.
Yeah. All right.
And it's just to spread. I mean, before they stack it, they line it up by what's in the sky. Okay, they line up the stars with each other, which means that, and then when you stack them, so that means a particular star is not always going to be an exact same pixel on the camera in each one of those frames that you stack it. And so, like Bill said, the statistical part of what's the value of that pixel supposed to be isn't based on whether that one pixel in the image is supposed to be, isn't based on how good a single pixel on the camera is, because it's been spread around multiple different pixels in different frames by the dithering.
That's a much better explanation. So like if the tip of my pen, you can't see it, is a star, and I move it around and I look at the pixels that made up that image, it'd be really easy for me to see, oh, I've got 0.8, 0.8, 0.8, 0.8, 0, 0.8, 0.8, 0.8. Oh, I'm going to throw out the 0 because as it was moving around, I hit a dead pixel. I'm going to throw that pixel out of the stack.
Yeah, DSLRs were notorious for having walking noise that you couldn't get rid of without dithering.
There's a really cool example on, I think it's Photoshop's website. This guy set up a camera to take a picture of a statue in Washington, D.C. And the problem is crowds are walking by the whole time, and so he couldn't get the image. So he just set it up there and just set it to take pictures every few seconds. And so people came and people went, and then he stacked it up and did a median filter, and all the people are gone. All that's left is the fountain, because it didn't move. All his quote defects came and went.
So I mean, I guess a question I've always thought is, if you measured the full width half max or the HFR of a stack of images, what number should you be shooting for in terms of how many pixels the stacked image full width half max ought to be? Should it be like 4, 3? Does that question even make sense?
Well, I think it makes sense to me if I think of it this way. What's the very, very best I can do? Well, the very, very best I can do is determined by the aperture of my telescope. So for me, that's something like, again, 2.33 lambda f number. So let's say it's the very best I can, the spot size is 5 microns. That's the best I can do. Then there's really no benefit, or not much benefit in my situation, to being a pixel size less than 2.5 microns. Now, my point about some of the presentation is that's only one part of the picture. It's really how big is my blur? Now your question is, okay, it was a different question. If I think about the blur size, and let's say your blur size from the optics, the very best you can do is 5 microns. then you know, the question is, how hard do you want to push everything else to get there? How much money do you want to spend to get as close as you can get? And one way I've been thinking about it is, if I multiply that number by 2, why? Because of the atmosphere. So not multiply by 2, maybe I multiply by 1.4. I'm going to use the RISS, whatever. Instead of 5, because of the atmosphere, maybe I'm really at 8. Now, how much money do I want to spend on my mount and my optics to keep that full width at half maximum day? Or maybe I decide I certainly don't want to give up so much resolution that my spot size is more than 3 times my very best possible spot size. So I don't know that there's a great answer that I have. For me, I would look at it in terms of, I got the scope, gives me a 5 micron spot size. Really like everything else to be not more than, add more than 10. And seeing is going to be one of the bigger elements of that. You know, I'd go back to Nyquist. What Nyquist would say is, it depends on what you're trying to see. So if you're trying to image really small double stars or small, tiny planetary nebulae, that's full width half maximum is really important. And you want it to be much smaller than the diameter of this tiny planetary nebula. You maybe want 10 full width of half maximums across the thing. On the other hand, if you're doing wide angle stuff that looks at dark nebulae, Barnard objects, well, you can get thousands, maybe several thousand full width of half maximums across that, and it's just much less critical. Yeah, I don't know. I don't have a good answer to that question.
So after the meeting, I'll check and see if Ron posted that article yet. He told me that he does that typically the month after the issue date, but I don't know. They've already sent out the March paper copy. So if it's not on his site, I'll just post a link to it in the group. Anyone that's not in the group, if you just reach out to me, I can send it to you. Thanks, Phil. Yeah, one of the new things that came up in the last month or so was PixInsight came out with a new version, multiple versions, and one of the newer features they have was a new gradient tool that relies on some databases that they're creating. And so I asked on the group if anyone wanted to talk about some of their gradient tools now that they've recently changed. And Dave said he'd like to do it. So I'll pass it on to Dave.
Yeah, I'll try to share my screen and get to that data set. Let's see. Sharing. Is that working okay?
Yeah, we got your whole screen.
Great. All right, let me get some of this stuff out of the way. So the origin of my interest in this was about December 21st. I set up the telescope in my front yard to get a picture of the sun in the daytime, for the solar challenge, NASA solar challenge. And that worked okay, got some images, but, and so I just left it there. And I normally don't try to do much at all for my front yard because of tons of trees and a very narrow window of visible sky above the roof. But it was there and I had some time, so I went ahead and tried to find something in my narrow window to look at. It turned out to be M110 was available. So ended up with about 110-second exposures of middling quality. And when I went to look at them, it was pretty bad. There are a lot of branches in there. I'll show you that in a second. Branch shadows, and it's tracking not great because I don't really have a proper polar alignment I can do. But anyway, it was better than I expected I might get, in fact. And so I had this data, and I had looked at it, and then I saw that PixInsight had finally released their new version, which included the MARS database. So what is the MARS database? MARS stands for Multi-Scale All-Sky Reference Survey. And just in a nutshell, what that amounts to is them and some volunteers also taking some wide field images under controlled conditions. A lot of it was with 35 millimeter camera, in order to get a survey of the background, of the sky under really dark sky conditions. They wanted some high quality dark sites to take this from. And and this was in pursuit of being able to use those data to subtract out gradients in a fashion that one of the PixInsight folks, Vicent Paris, had developed a algorithm for, which isn't that complicated, but I'll get into that a little bit. But first, I just want to show you this, how it worked out for me to use this based on these data. So here's there's about 100 frames. And if I use the blink tool in PixInsight here, hopefully you can see this. I'm just going to step through these. There, it's moving. Oh, and then hopefully you can see these shadowy features. And there's a little bit of drift, in the image. You've got Andromeda there on the left side. Well, it's gradually going out of the frame. M110's still in there. But in the background of this, there's, again, all these tree branches I was looking through. And to add to the misery, there's the nice big branches that got really low. To add to the misery of this, I have a huge street light in the center of the cul-de-sac right in my front yard. So there's all that is going on as well. Maybe it's not so obvious in the blink, but it becomes obvious later. So I'm showing you that because that's the raw data here, the light frames that went into this processing. So let me get rid of that for a bit, and this and the blink. What I wanted also to show is that the majority of getting rid of the branches and all that, a lot of that background that was in those frames came from using this weighted batch pre-processing script. So here's the current version of weighted batch pre-processing. All those light frames are in there, every last one of them, even the really crummy ones at the end. I did include a flat frame correction, dark frame correction, standard stuff, nothing fancy. And I just checked all the boxes here and let this weighted batch pre-processing do all of its features, which include, some defect correction, that's kind of minor, image registration, but it spends a lot of time on local normalization, which, again, I just ran in the automated mode. Importantly, it integrates them and very importantly, it gives you an astrometric solution, which is absolutely necessary to do any of this multi-scale gradient correction. In short, the data, the database needs to know which part of the sky you're looking at in order to line up appropriate background that's there. So I'm not gonna run this in real time because it took about on my computer about 19 minutes to get through all this, but I'll show you the result. I think it's this one. Yeah, the result was like this, which is, well, actually on my screen, it pops up green initially, and then you do a control screen transfer function to put it, you know, with appropriate colors. But you can see there's a huge glow here of red. Probably this could be the street light, I'm not sure. Whole bunch of color mismatch, and a lot of stray light all over the place. I kind of like the framing though, because it's got this cool, you know, side of Andromeda plus M110 centered there. It looks nice, but needs some correction. And then, so the current version of PixInsight is the following. If I click on this, and just so you know what to look for if you want to mess with this, it's Lockhart. So they've, in addition to giving them numbers, version numbers, I think this is the first time they've added a name, just for, you know, shorthand convenience of talking about which version. This is Lockhart, and they started out with 1.9.0 and they're already up to 1.9.2. And I'll, as an aside, this is running on a Linux machine, but just a few days ago, they released a Lockhart version for the Mac operating system, which wasn't there initially. So they have all the platforms covered now, all three of them with this version. If you wanted to go download it, you know, downloading and install is the same as usual. Nothing out of the ordinary, but you do have to download the MARS databases from the same place you would get this software, but that's straightforward. You just park those in the same place as your program and go find them. So so this is kind of the starting point here of applying this gradient correction. The idea being that if you normalize the light intensity of these stars properly, and there's a tool for that, then you can, using some pretty simple pixel math, essentially you're subtracting out this background quantities from the database that they supply. And the fact that the database is a very wide field data set compared to the more narrow field of view in most people's images, they're able to make that work pretty reliably, because the differences in sky background, you know, over a large field are relatively small slopes compared to what you're looking at here. It's not perfect, but you know, it shows a lot of potential, I think. And I am not, you know, gonna argue the value of this in all instances, but my sense is that it's going to be most valuable for images like this, where you have a few fairly bright objects of interest, such as these galaxies. It will be more challenging to apply the more faint your target of interest is relative to background. And that just sort of makes common sense. Is if you start, you know, subtracting too much from a small signal, you could get into trouble. But so here's kind of your starting point with an image that is in need of background correction. And what I did from here is apply this tool here called spectrophotometric flux calibration. Oh, sorry, that's not the one. This one. This is important for calculating, in some sense, that the software needs the intensity of the stars. In my notes here that I pulled from PixInsight, they make an important point that the spectrophotometric flux calibration doesn't change the data. It changes the metadata in this file, which is then grabbed and used as part of the pixel math function to subtract the background. Depending on what filters you have, this is where you would enter them. It's the case currently that there's only RGB and luminance and H-alpha data in the database. There's no O3 yet. There's no of the other typical filters, but those are coming in some future release of the MARS data. So they say, and I'm sure that's true. But right now, you're pretty much limited to the RGB and I guess H-alpha you could work with. But this is kind of the first step. You need to have an astrometric solution to apply this, but then you would just go over here and drag your flux calibration in there and let it run. This goes pretty quickly. And then produces an analysis of how well you fit that. And that should have popped up here. It's kind of blank. Well, this amounts to a curve that kind of shows the range of star intensities that you have. And to me, it's effectively a normalization of that. Not quite sure why it's not showing up here. It could be that I've run through this a couple times and it's caused it to misbehave. But let's not worry about that so much. So I get to the main show here, which is the multi-scale gradient correction screen. So this with Lockhart, this becomes just one of the processes in the process list. It's important for convenience to go to this preferences box early on and add in the MARS database files, MARS database files here. That's straightforward. So then after having done that, then they'll be available here. If you want to apply, so this is the main one here. This one here with the U in it is user supplied data. And since you guys are pretty advanced process imagers, you may be wanting to do this on a part of the sky for which there is no background data yet. And you can supply your own reference image here if you wish. And it'll apply that. As long as I guess you've taken that reference image with a wide field camera with appropriate other parameters, which I haven't really looked into, but I think those are available on the PixInsight website as far as how to generate that reference image for yourself. You could apply your own. I've certainly not done that. What I have done is apply this multi-scale correction and a few different times. And there's a couple other parameters here to work with if you didn't like the default result. All these are default parameters with the exception of gradient scale. The default gradient scale is this value 1024, which effectively means that the larger that number, the less sensitive it's going to be towards small gradient features. As you lower that gradient scale, it's going to do a better job with smaller gradients, portions, and removing them. And that's kind of demonstrated in this set of gradient models. So as you execute this gradient correction, you do want to check this box that says show gradient model, because that's going to produce a file like this one. So for 1024 gradient scale, for example, and if you run it, you end up with a gradient model that looks like this. Let me pull this over. And you can kind of see what it's subtracting out as background is there's a huge red blob here with corresponding to my red blob here. There's some green as well in this region that sort of makes sense. And so to execute it, it's pretty simple. At that scale, you just grab the corner or hit execute. And it runs pretty quickly. I was kind of pleasantly surprised that it wasn't bogging down forever to generate this result. Get that out of the way. So that's done, 10 seconds. This should be the gradient model. Oh, there's the new corrected image. So at a scale of 1024, it did pretty well. It removed a lot, but I can still see some reddish patch here. This green's not so great, you know, and there's some other reddish patches of who knows what background from my street lights or looking southeast into the city. So what I ended up with finally liking the result from changing this gradient scale down for this particular image down to 384. And when I did that, you know, I got this sort of gradient model for subtracted, and you can see it's significantly different than the first one. And I think this image here is the result of that correction. Oh boy, all that stuff here. Let me hide that and expand that. So this is the one I liked best. But it definitely helped to move for this particular image. It helped to move down in image scale, or the gradient scale, I guess they call it, to improve the quality of background subtraction. It's not perfect, and I think it's wise to maybe do this and then do additional background normalization with other tools if you wish. One video I saw online from SETI Astro showed a lot of playing around with the scale factors here to improve things. I have not done any of that yet, or tried to work with the structure separation parameter yet, or model smoothness yet. But those might benefit this and other images as well. I was happy enough to get this, considering all the branches and stray light I was dealing with, called it good enough for now, and motivated enough to volunteer to talk about it, because I don't know, a lot of people deal with stray light issues and weird gradients. You never know when that's going to happen, especially if you're, you know, in a new place or you don't have control over some lights. It can be pretty handy. And so so far I'm happy with it, and it ran pretty smoothly and cleanly and really pretty fast. It's not a slow process, and you know, there's a fair amount of reference data, mostly article online on PixInsight from Vicent Paris about his algorithm that's very readable and might, you know, it's a little bit over my head, but not too much, and worth another read by me to understand more fully. But you can see it's pretty easy to execute, and then you just go from here with your, you know, normal steps that you might use in PixInsight. Like from here, I just did the you know, background normalization, color correction, and then stretching, blur exterminator, that sort of thing can all be done after this stage. This is all in linear data still. I think that's about all I had to cover here, but I'll take any questions if you have some about it.
Anyone else tried this one tool?
I tried it once. My image didn't have nearly the kind of gradients that Dave's did in it.
Yeah.
And it was more of a one-shot color with a lot of nebulosity HA in it. And the only thing I didn't like about it, and you can kind of see a little bit of it in Dave's, is it kind of like right on the edge of M31. If you compare the final one to this one over here, it seemed to subtract out some of the faint halo around M31. And I found that when I ran it on my image, it seemed like it subtracted out some of the dimmer nebulosity along with the gradients, which I think that's probably just a classic problem with gradients, is figuring out what's the difference between a gradient and dimmer nebulosity. And I think it depends on the calibration images that they're using. It's if the image you're trying to subtract a gradient from is deeper than the reference image, then you're going to have features in your image that aren't in the reference image, and it's going to think it's background, or think that it's gradient and not something faint you were trying to draw out. So I didn't play around with all the numbers. I didn't even play around with the number that Dave played around with. So I don't know how much of that you could control. But
yeah, so I sort of have the feeling that you could potentially have really good control over that. Just from mostly just a couple of YouTube videos I saw that where they were looking at some faint nebulae and trying to tease apart the difference between background and the actual target data. But that's clearly going to be the big limitation of any tool like this. You subtract too much, that's wrong. You want to subtract the just right amount. And their whole theory about this, I guess, is that this survey of the sky should be the real deal. Since if it's done in a dark background, that should be the expected background. Whatever else you have coming from your observation site that's not so pristine, can theoretically be subtracted out. But you've got to get the parameters just right. And then maybe using this tool doesn't preclude using other background removal tools in PixInsight, which I don't pretend to be that familiar with. I've used a couple of them. Usually I just go with the automatic background, but that's clearly not enough in many cases. My hope is that this will be kind of more universal and easier to apply. Time will tell.
yeah, I'm not saying that don't use it or anything. I just that was the one thing I noticed most about it was I seem to lose, and I have that problem with almost all the gradient tools that I try to run, is it seems to try to take out what I think is faint nebulosity and not gradient. But
Right. Well, the one thing I guess I'm surprised just looking at this in front of me, this is from a one-shot color camera, and it really is dealing with the color oddities in the background in a way that I didn't really expect to do. I think for me, for this image, it might be worth me playing around more with some of these other factors and scale factors and see if it could be made even better. But the only thing I do want to emphasize is that I think a lot of the benefit of the processing of this crummy data set was done in the weighted batch pre-processing. However, it did the stacking and some level of normalization of that eliminated all those tree branches and left me with a pretty good set of stars. I was not expecting that really to be so good, and that is not really what I don't think this MARS database and all the tool is really doing much with that. I think the pre-processing took care of a lot of ills in this data set.
Well, that large number of subs that you had for that helped tremendously on that in that part of it.
Yes, for sure.
You can use much more sophisticated rejection tools on it than it
Yeah,
can't with a small data set.
yeah, that would be interesting experiment for me to do is just take instead of 100 frames, take 10 or 20 and see how it does. That'd be worth my time to check that out. I don't know how that'll go. I just threw them all in.
Can you make
that
those
was 110-second frames?
Yes, 100,
Oh,
10-second exposures, right?
wow.
can you make those background models 24-bit?
Yes, I can. So let's see, let me bring this one up here on the other one. There's a whole series of them if you want to look at them all, but there it is. I kind of like the more blocky version for illustration, but this is kind of how most people like to look at them, to smooth them out.
I was just wondering what that extra blue down in the lower left corner was from.
Great question. Yeah, it's definitely there. And well, let's see. Where's the original? Hang on. Maybe I can undo that. It's not so obvious what that blue blotch right there might be, but it did find it, and it's in both gradient scales. I'm not sure, but yeah, I was surprised that it was doing the subtraction in a color color specific manner. But maybe I shouldn't be. Yeah, that is kind of part of what you're doing is dealing with different colors.
Yeah, I think it does a pretty good job. So, I mean, it's fairly new.
Yeah, it definitely. And there's not even I didn't find that many examples out there yet of people applying it or even talking about it.
Right.
Um, Clearly, they're planning a better, more expansive release of the All Sky survey with more filters and larger image scale. So in the tutorial, in the PixInsight tutorial about it, they're clear that right now it's limited to a fairly narrow field of view. Specifically, don't try it with anything greater than 5 degrees. It won't work. And that's just because I think the background the survey data was, I think they said 22 arc minutes wide, or it's a fairly wide field of view, but it's not so wide that it can handle every large field of view image you might try to process. It'll break down. But yeah, and hopefully O3 data in there at some point, but not yet.
Dan, I sent you an image today that compared this new tool with Graxpert. I downloaded both of them for the first time today and tried them with the new release of PixInsight. Would you be willing to throw that up there and talk about it? It's an H alpha image, so it's monoscale, but these two different routines compared very well.
Yeah, hold on. I'm looking for it. It's on my desktop, but it's behind all these windows. Okay.
I need to unshare or
I don't know. I've got some new version here, and it looks like it's
I'll stop sharing and you can put that up.
Is that the one you sent me, or is it?
Yes, that's it. And the one on the left is the new PixInsight routine, and the other on the right is the Graxpert that you can find in the toolbox and under the scripts pull down. So this was done, I guess I should have sent the original image. This is just the gradients that these two tools found in that image from Dark Sky, New Mexico, where we don't really have big gradients. And of course, the 24-bit versions look a little smoother than that. 24-bit versions look smoother. But I thought that was, qualitatively pretty similar.
So how did the image result look? About the same or what?
I couldn't tell a difference. I blinked the original with the corrected image in both cases. I couldn't see any difference. The gradients were that small.
Mm-hmm.
For what it's worth, Graxpert has a standalone version. So if you're not a PixInsight user, you can still run Graxpert. I use it on SeeStar images.
Correct. Yeah. I used the PixInsight version today, but I downloaded but didn't actually use the standalone version.
Yeah, when I was reading, a lot of people use Graxpert and like it a lot. So that's maybe
Me.
Yeah.
Yeah. So the fact that this one got similar results, that's encouraging for both tools.
Oh, and I'll add Graxpert is free and it does noise reduction too.
Free is good. Nothing wrong with that.
Hey, Dave.
Yeah.
I was wondering if you've ever heard of anybody having trouble with like an aurora messing up their photographs. There might be auroras that aren't very bright that you can't see with your eye.
Well, not me, but Dan's had that problem.
Yeah, they actually look like a lot like your image with the odd colors in it. When I was first learning, one of what I considered like my mentor was this guy that had a big LX 200 in a place called Mantrap Lake, Minnesota. And the guy complained, he was like Archie Bunker. He complained about everything. His camera couldn't cool enough because it would only go down to minus 35 degrees Celsius and it was too cold up there. And then he complained about other things. But one of his biggest complaints was the aurora would mess up his images a lot of the time. And I actually shot the last time, a couple times back when we had some down in New Mexico, I tried to shoot over the top of them and it didn't work so good. They had weird red gradients throughout them, but yeah.
Yeah, I guess a aurora or just maybe high clouds reflecting, different color lights that are predominant for the city or area. You're getting all those reflections off of. It's just really high stuff. That you generally look up and you think it's clear, but there are clouds there. They're just really thin and really high.
Down in
So I
New
guess you
Mexico,
can get
in New Mexico, Dan knows this. We have an all-sky camera, and we frequently see bands of air glow propagating across the hemisphere above us, green waves. And those can, if they aren't symmetric over your subframe times, they can give you some gradients. So you're kind of joking about aurora, but air glow is pretty common, and that does affect our gradients down in New Mexico, probably almost as much as anything else.
Yeah, my question is, how do you know you're getting rid of some artifact versus some, hydrogen alpha nebulosity that's, there, and everybody else sees it and thinks, oh, that's an artifact. So they get rid of it too. And
Well, that's why this Mars database is supposedly good, because it doesn't include those nebulae, but it's to be seen if that really works out well or not.
Mhm.